In this tutorial, we are going to make use of the compound, reduction and double angle formulae to solve some typical examination questions. I've got these this one question here which is made up of two parts, and we have to convert or reduce these expressions into in terms of P. So the first one is going to be cos of 334 multiplied by sine 244. How can we write this expression in terms of P? You'll notice that 334 is a fourth quadrant angle. So if I were to draw something like this, so we know in our cast diagram that this is going to be 0, 90, 180, 270, and it goes back to 360 degrees there. And so this angle is going to be equal to 334 degrees. Well, we want to see how we can write this cos of 334 in terms of sine of 64, because that's what we are given there. Well, you'll notice that if I do 270 plus 64 degrees here, this one here is going to be equal to cos of 334. So cos of 334 is the same as the cosine of 270 plus 64 degrees. But you know, using your reduction formulae, that the cos of 270 plus some angle theta is going to be equal to the sine of theta. Okay, so it follows therefore that the cosine of 334 will be equal to this cosine of 270 plus 64, which is essentially just equal to the sine of 64. You can use your calculator to check that this is actually true. So in place of cos 334, I'm going to put sine 64. Let's have a look again at sine of 244. What can we reduce that one to? Sine 244 is the angle 244 degrees is a third quadrant angle. So if you did this, you will notice that it's going to be somewhere there, because this is 180 and this is 270. So I know that it's going to be a third quadrant angle. So I could add 180 to some number to give me 244, and you know that this is going to be the same as the sine of 180 plus 64. But you know from your previous work that the sine of 180 plus theta is simply going to be equal to minus sine theta. Okay, we expect sine to be negative anyway in the third quadrant. Remember, your cast diagram goes like that. So it is going to look so now that we've been able to reduce this in terms of well, we haven't. We want to say that sine of 180 plus 64 is actually just equal to minus sine of 64. Okay, so now we've managed to reduce this into terms of what? Sine 64. So therefore cos of 334 multiplied by sine of 244 degrees is going to be the same as, so this one we worked out to be equal to sine 64, and that is going to be multiplied by minus sine 64. But we both know that sine 64 is p multiplied by negative p, and therefore that expression is equal to minus p squared. In the second question, the approach is very similar. What we are trying to do is find what this expression is going to be equal to in terms of P. So here, this here already shows us that it takes the form of the double angle formula of sine. So we know that the the sine of 2 theta is equal to 2 sine theta cos theta. This here you are given in your formula sheet, and we can actually write this one as 4 multiplied by 2 sine of 16 cos of 16 multiplied by cos 32. Alright, so 4 times 2 gives me 8, so those two expressions are equivalent expressions. So it follows then that I'm going to have simply 4. 2 lots of that is going to be 32, so it's 2, it's sine 32, so sine 32 multiplied by this cos 32 again. So again, you can see this is the double angle formula for sine, and I'll have to do 2 brackets 2 sine 32 cos 32. Alright, and so it follows that we are going to have this being equal to 2 sine 64. But sine 64 is given to us in the question as p, so therefore the final answer is going to be equal to 2p. The question could sometimes be asked in a slightly different way, as in this next example here, but essentially the examiner is still trying to see if you can apply your compound or double angle formulae to a given problem. So let's have a look at this one here. It says sine 43 is equal to a, and cos of 90 minus k cos 23 plus that is equal to b. Then we need to find the value of k if a is equal to b. So if a is equal to b, it simply means that the sine of 43 is going to equal this expression here, the cosine of 90 minus k cos of 23 plus the cosine of 246 sine of 23. Alright, so we need to determine this value of k. This expression, you can see, it could either be the compound formula for cosine, because you've got to cos some angle and cos some angle, cos some angle and sine some other angle, 246 and 23. So it's of this form here. Remember, these formulae are given to you in your formula sheet. So it says b there is going to be identical to the sine of a cos of b plus or minus the sine of b cos of a. Okay, so this is what I'm saying to you. This second part here looks very similar to that, and the other one is this one. The cos of a plus minus b is identical to the cos of a cos of b minus plus the sine of a sine of b. So we need to make it look like one of these two identities. Now, you know this is a complementary angle, 90 minus k. You know again that the cosine of 90 minus theta is going to be equal to the sine of theta. They're complementary angles. So if I were to proceed, this is going to be the sine of 43 is going to be equal to, that's just sine k, multiplied by cos of 23 plus, well, we need to do something about this angle 246 and make it into an acute angle, because, well, often this angle A and B in this compound angle formulae are acute angles. Now this is a third quadrant angle, and we know that cos is going to be negative there. So, but anyway, I could write this as the cosine of 180 plus 66 sine of 23. Alright, and so this is going to stay the same. I still have sine of 43 is equal to sine k cos of 23 plus this here. We have agreed that this is simply going to be equal to negative cos of 66, and we're still multiplying this by the sine of 23. Now have a look. This expression is now of this form here, sine k cos 23. A positive times negative is going to be a negative, and let me write it like this: sine 23 cosine of 66. Now this is of this form here. It's a compound angle formula for sine. Okay, so if this is 23 and that is 66, is k going to equal 66? Okay, let's see. If I went here and said to you that sine of 43 is the same as saying 66 minus 23. So 66 minus 23 is indeed 43, so I haven't changed anything. So that becomes my angle A, and this becomes my angle B. So this is going to be equal to, in this expansion, it's going to be sine A cos B. So sine A, it means that sine 66 cos of 23 minus sine of 23 cos 66. Well, comparing expression 1 to expression 2, all these other terms are the same, so it follows that this is going to equal that. So therefore k must be equal to 66 degrees. The last example in this tutorial is going to be an identity, and we want to make use again of the double angle formulae to try and prove that this expression is true. So as before, you know that you've got to take one side of the identity and reduce it to make sure that it is equal to the other side. So you're not allowed to move terms from one side to the other. Generally, you want to take the side which is more complex. That means you've got a lot of things to do to manipulate it and try and reduce it to the right hand side. So evidently in this one here, the left hand side is the most complex, so I'm going to take that and try and make it into 2 over cos theta. So when you have a look there at the bottom, you've got cos squared, sine squared, and I want to end up with just a single cos on the right hand side. There are different variations of this identity, but I'm going to take this one here. Again, this identity for cos 2 theta is given to you in your formula sheet, and so it's going to be equal to cos squared theta minus sine squared theta multiplied by cos theta. Well, on second thought, it looks like it's easier to actually just substitute this into the double angle formula that I'm making use of here. So you know that cos 2 theta is identical to cos square theta minus sine square theta. Right, so it'll be shrewd to make the substitution in the denominator and not in the numerator. So let's do that instead and have 2 cos 2 theta multiplied by cos theta, and that whole thing is going to be equal to cos 2 theta plus tan theta. You and I know that it's going to be the same as the sine of theta divided by the cosine of theta multiplied by the sine of theta, and this is over 1. So I'll proceed to doing this. These are common terms, they cancel out, so I'm going to have 2 cos theta plus the numerator multiplies the numerator, and the denominator, giving me sine squared theta, all that is over cos theta. I'm going to endeavor to write it as a single fraction because the right hand side is also just one term. So let's put this into one term. The lowest common denominator, or LCM if you like, is going to be cos theta. So we have cos squared theta plus 2 sine squared theta, and that whole thing is going to be over cos theta. Alright, so we factor out at 2 and we'll have cos squared theta plus sine squared theta, and this thing is going to be divided by cos theta. But you know that cos theta, cos squared theta plus sine squared theta is simply equal to 1. That's one of the Pythagorean identities. So 2 times 1 is going to give me 2, and that is over cos theta. And this thing is exactly equal to the right hand side, and so we've managed to show that that identity is true.